Okay, so today we are going to be talking about eigenvectors. So recall that if I have a linear transformation T or matrix T and I let T act on a vector V, we get a vector W which may differ in magnitude and direction from V. Now, there are special kinds or special class of V for which the action of T on V doesn't change the direction of V, but rather just scales it along the same direction as V. So we write that as T of V equals to just some constant times V. So this is a scalar. So what does that look like pictorially? So let's say I have a linear transformation T which acts on R2 and brings it to R2. So we can take a look at that. So let's say I have a vector V1 and the action of T on V1 just brings it to the reverse. So this is T of V1. We can write that as T of V1 equals to minus some constant V1. So in this case the lambda corresponds to this negative C and V1 is our V in this case. So if we can find a vector V that satisfies this, we say that V is an eigenvector of T with eigenvalue lambda. And it's standard convention to call the eigenvalue lambda. Alright, so let's do an example of what eigenvector looks like for a particular example of a linear transformation. So let's say we have a line in R2, and you'll recall that a reflection across this line is a linear transformation. So let T be the reflection across this line. So if I have a vector V1 which is along this line, the action of T on V1 does nothing to V1. So you can write that as T of V1 equals V1. And if we wanted to be explicit about the form, putting in the form that we had just now, this could be written as 1 times V1. So we say that V1 is an eigenvector of T with eigenvalue 1. And similarly, if we define V2, which is perpendicular to this line, the action of T on V2 is to reflect it, and we can write that T of V2 equals minus 1 times V2. So V2 is an eigenvector of T with eigenvalue minus 1. So immediately we should be able to think of some properties of eigenvectors. So let's say I have a linear transformation T and I have an eigenvector of T called V1. So eigenvector of T with eigenvalue lambda. So it should be clear that any constant times V1 is still going to be an eigenvector of T with the same eigenvalue. So if you write that out, so because this is a linear transformation, we have C of T of V1 equals C of lambda V1 equals swapping these scalars. So any constant times eigenvector of T is going to give me another eigenvector of T with the same eigenvalue. Now a similar concept is that if I have two vectors V1 and V2, which are both eigenvectors of T with eigenvalue lambda, then any linear combination of V1 and V2 is going to be also an eigenvector of T with eigenvalue lambda, and these lambdas are all the same. So you should be able to prove that to yourself rather easily. a slightly less obvious concept that you might not have thought of is that if I have an eigenvector v1 and another eigenvector v2 of t with different eigenvalues, so we have t of v1 equals lambda 1 v1 and t of v2 equals lambda 2 v2, where lambda 1 does not equals lambda 2, then we can say that v1 and v2 are linearly independent. So these are linearly independent. Okay, so how do we prove that? The proof of that is actually rather simple. So the first assumption we make is that lambda 1 is not 0 and lambda 2 is not 0. So you may ask, what happens if one of them is 0? That's an exercise to the reader or the watcher. That's actually rather simple. So let's say they're not 0. Okay, what do we have? And we assume that, say, c of v1 plus d of v2 equals to 0. So we want to prove that they are linearly independent, which means that we want to prove that c and d must be 0. So we multiply this whole thing by t, and that gives us t of 0 equals 0. And if we bring t in, we have that c tv1 plus d tv2 equals 0. Okay, and we have that lambda 1 cv1 plus lambda 2 dv2 equals 0. Okay. Now, I shall leave the last line here. Now recall our original equation. It should be c of v1 plus d of v2 equals 0. Now, if we multiply this whole thing by a scalar, say lambda 1, we get lambda 1 of cv1 plus lambda 1 of dv2 equals to lambda 1, 0 equals to 0. Now, if we take this minus this, what do we get? So this term cancels out, and this term becomes lambda 1 minus lambda 2 d of v2 equals to 0. So this term, is not 0 because lambda 1 is not equal to lambda 2, so this is not equal to 0. And this term might or might not be 0, but we know that this is not 0 because recall that our eigenvectors cannot be a 0 vector. Otherwise everything will be an eigenvalue of t. So what we have is that d of some non-zero vector, which is lambda 1 minus lambda 2 v2 equals to 0. And that brings us to the conclusion of proof where we have to conclude that d is 0. And to prove that c is also 0, you can just substitute d in, and you get that lambda 1, or rather you get that c v1 equals to 0, and you conclude that this is also 0. So that's an example of a slightly more non-obvious property of eigenvectors that you might not have thought of.